Today we're looking at the basic combinatorics. What that means is the combinations of something, how many ways something can occur. And when we're looking at the number of ways something can occur, it's used a lot when you deal with any sort of probability or statistics. It's used a lot. There are three different types of combinations that we're going to look at. The first one is what we call the fundamental counting principle. And this is kind of the basic one that you probably would have learned maybe clear back into middle school. The thing to remember is, and when it's kind of tricky for this combinatorics, is knowing when to use which type. So the fundamental counting principle is used anytime that the order is important. So if you mix up the order, it's considered a different combination. And the biggie that you are allowed to do in the fundamental counting principle is that you can repeat values. For example, if you're trying to figure out how many different license plates are possible, I usually do my fundamental counting principle with some dashes, and I would look at it, okay, I can have 3 letters, 1, 2, 3 letters, followed by 3 numbers. And then I fill in the blanks with how many options there are. So how many letters can I use? Well, there's 26. And for the second letter, since I am allowed to repeat on a license plate, I can use a B twice in a row, and that's no big deal. Then I would still have 26 options for the next one, and then 26 options for the last letter, followed by 3 numbers. Now there's 10 digits, 0 through 9, so I'd have 10 options, and 10 options, and 10 options, because I can repeat. And what I'm doing in here is I'm multiplying. That's what the fundamental counting principle is saying, is that you can, however many options you have for the first one, times however many you have for the second, and so forth, would equal your total possible. So I'm just going to type that in my calculator as 26 to the third. And then since it's times 10 to the third, I'm just going to add 3 zeros. I end up with a possibility of 17,576 different license plates that can be created. However, you actually can have license plates that put the numbers first and then the letters. You would also have the possibility to go 10 times 10 times 10 times 26 times 26 times 26. Well, that's going to give me the same number, so I'm still going to be at this. So then if I add those two together, I actually end up with then a total of 35 million different license plates that are possible. All right, this idea right here of multiplying the different ways something can happen is called the fundamental counting principle. So if you look at how many different phone numbers could we create? If you're just talking a 7-digit phone number, how many options do you have for the first number, the second number, the third number, and then the 1, 2, 3, the following 4 digits? This is a little bit trickier, and we talked about some exceptions in class. Without going, I guess if I just was very basic and said there's no restrictions whatsoever, I'd have 10 possible digits, and I can certainly repeat numbers in my phone number. So I could sit here and just multiply by 10 7 different times. So that's just 10 to the 7th. But there are some restrictions, and there actually are restrictions with license plates as well, but there certainly are with phone numbers. You cannot start with a 0. Nobody's phone number starts with a 0. Because back in the day, and probably still does, it calls the operator. And the operator, of course, is probably a computer now, but you still can't start with a 0. You also cannot start with 1 because, again, if you think of like a landline, if you still have a home phone number or a home phone, if you dial 1, it's the beginning of calling long distance. So there are restrictions, and then we talked in class about how you start limiting that. Well, if this can't be a 0 or 1, now that's going to be an 8 instead of a 10. But then the rest of them could still be 10. Now this 10 to the 7th that we came up with is just 7 zeros. So that's 10 million. If I were to change this to an 8, then it would suddenly be only 8 million different phone numbers. And there's other restrictions involved with that. Then it gets a little bit trickier, but that's the basic idea. Okay, how about this last one? How many ways can you answer a 10-question multiple choice test? All right, you're just walking in. You forgot to study. You're just totally guessing. You have no idea what it's about. Well, you have 10 questions. How many options do you have for the first question? Well, it could be A, it could be B, it could be C, it could be D. I have 4 different options. And for the next test, or I'm sorry, the next question, well, I can repeat. If the last answer was A, it could still be A, so I'm still going to have 4 options. And I'm going to have 4 options over and over, and really that's just going to be a 4 raised to the 10th power. Which is 104,875.76. A million different ways to answer that. You should probably study. That was fundamental counting principle. The second method that we use is called permutations, and the word permutation means an ordering of objects. So you're looking at how many different ways you can put something in order. Obviously, then, the order that you put them is important. What's different now is that you cannot repeat, which is okay. Repeating is not always allowed. For instance, if you go to a dog race or horse race kind of thing, if you think about that, how many different ways can these dogs place in a race? And the way we think of it is, well, there's 8 dogs racing, and I have to choose all 8 of them in order. How many options would I have for the winning dog if I picked the first dog? Well, there'd be 8. But the deal is once I've picked one of those dogs, I can't pick it again to place second or third. It's done. So I'd only have 7 options for the next one. And then I'd have 6, and then I'd have 5, and 4, and 3, and 2, and 1. All right, that would be permutations of 8 items, and we're going to choose all 8. Those are little sub-numbers. Sometimes you don't need to pick, and in fact you don't. And remember I said that this whole idea of these combinations works a lot with probability, and probability is what drives gambling. So when you look at making a bet, the more ways something can happen, the harder it is to pick the right way. So that'd be a better winning type of bet, but it'd be hard. Well, I say better winning. The winnings, like your prize money, would be very high because it would be very unlikely that I could pick all 8 of those in order. You can type that in your calculator and see what 8 times 8 all the way down is. Actually, let me backtrack. Maybe I better tell you how to do that in your calculator. We're not going to take the time to go 8 times 7 times 6. There's a button. It's really just called 8 factorial. It looks like this with the exclamation point, 8 factorial. And you type that in your calculator. Just press 8, and then you go to math, over to probability, and it's number 4. So 8 factorial, that's 40,000. 320 different ways to pick those 8 dogs to place. That'd be pretty unlikely that I'd pick that. Which is why there are other bets that aren't quite as impossible. What if you only had to pick the top 3 dogs? Well, there would be 8 options for my first dog, 7 options for the next, and then 6 for that third place dog. That would be written permutations of 8 items, and I'm just going to choose 3 of them. That is no longer this 8 factorial that I had up here. 8 factorial was equal to that 40,000. All of a sudden, I am now only using this much of the 8 factorial, which means I'm not using 5 factorial. When I do 8 choose 3, I'm basically taking 8 factorial and I'm dividing it by 5 factorial. And all that's going to be left then is the 8, 7, and 6. The formula then, when we do permutations of n items, and I'm going to choose r of them, I'm going to take the n factorial, and I'm going to divide it by n minus r. So if you look at this one, it was 8 minus 3. Factorial. That's where I got my 5 factorial. And that's a nice formula. We do happen to have a button that does this permutation. If you do this again in your calculator, you would type 8, and then you go to that math menu and over to probability, and it's number 2, permutations. And then I'd press the 3. 8 permutations of 3 gets me 336. There are 336 ways to make that happen, so that's way more possible than the previous method, and so of course, if I were to win this bet, I wouldn't win as much money because it's easier to happen. Now, what if the order is not important? For instance, let's say you're like one of the owners of the dogs, and in fact, you happen to own 3 of those dogs because you're way into this. I don't really care who the first place, second place, and third place dogs are, just as long as it's my 3 dogs that win those places. It doesn't matter which one's which. If that's the case, how many ways did my winning dogs get overcounted? In other words, if you think about it, if on that previous one, if I had Fido winning, and then I had Spot winning, and then I had Rover winning, to me, that's the same as if Spot and then Rover, and then Fido won. I'm going to win the same amount of money there. Or Fido, and then Spot, and then Rover is still a winning situation for me. Back to our question then, how many ways did that scenario get overcounted? Well, I just wrote a few of them, but if you think about it, how many ways did my F, S, and R all get picked as the top 3 dogs? Well, I have 3 options for that first dog. It was either Fido, Spot, or Rover. I have 2 options left for the next dog, and I'd have 1 left for that last dog. That's just 3 factorial. Every scenario of picking the top 3 dogs got overcounted by 3 factorial. Which means, this leads me to combinations. This is the third method. Combinations finally is going to be used if the order is not important. I still cannot repeat. I can't have the same dog finish more than once. But this is the one that we use when order is not important. And this is probably the most common one. It's used a lot like if you're playing cards, the order that you get your cards don't matter because you're going to rearrange them in your hand anyway. Now, since we had to divide by 3 factorial because we way overcounted, so that previous formula when this was a permutation, not a combination, it was a permutation, we had this n factorial over n minus r factorial. But now, if we want this to be a combination and order is no longer important, we would also divide by the r factorial to get rid of that overcounting. And just a little notation thing, because combinations are probably the most common one of these 3 different combinatorics that we're doing, we have a different notation that we use for it. It's supposedly a simpler, or really you see this just a lot more in upper level textbooks. But if you see, there's n items and I'm choosing r. This is not a fraction. Don't put a fraction bar in it. It's just n choose r without putting the big C in there. If you see this notation, it means the same thing as this. And we still have a button to do that. Combinations of 8 choose 3. I'm going to type 8, math, over to probability, and it's number 3. The combinations, choose 3. Okay, so now there's only 56 ways to make that happen. So by doing the combinations and taking away the importance of the order, your numbers are going to get a lot smaller when you do that. All right, those are the 3 different types. We have fundamental counting principle, permutations, and we have combinations. Let's look at a problem here that's a little bit trickier. In a scenario here where you have a lot of options, like you walk into Subway and they have 8 toppings. Of course, we know they have way more than 8, but let's just say they have 8 toppings available. And you walk up there and you're trying to decide what kind of sandwich you're going to get and how many toppings there are. Well, let's say I'm going to pick exactly 4 toppings. How many different sandwiches could I create? All right. When you're making your sandwich, it doesn't really matter the order that you put all the toppings on. It doesn't matter if the cheese and the meat and then the lettuce or lettuce, meat, cheese kind of thing. Order doesn't matter. That would imply that it's going to be a combination. That's going to be combinations there are 8 toppings and I'm going to choose 4. Or another way to write that is just 8 choose 4, like that. I'm going to go to my calculator, and I'm just going to type it in. 8 math probability choose 4. All right, there are 70 different sandwiches that I could create. How about this question? How many total different sandwiches are possible? This is a way more complex problem because it doesn't say that I have to get all 8 of them, right? I'm not getting all 8. I might only get 3. I might get 4. I might get 5. I might get 6. What that means is that I would have to look at the scenario where I just want bread. I don't want any toppings. I just want meat. That's what my kids always wanted. They just wanted the meat. They didn't want anything else. Or maybe meat and cheese. Or meat, cheese, and lettuce. And you could eventually keep adding more and more until you get up to all 8 toppings that you've added. But you have to look at this happening, or this happening, or this happening. And we would have to do each one of these to get, and then add it all up to get the total number of sandwiches that are possible. That's going to take me a while to type in my calculator. And not that I can't do it, I could. But if you'll recall, and you may or may not recall, Pascal's triangle is actually created from all of these combinations. And you would list out all the different answers to this. And that would be the 8th row of your Pascal's triangle. That's where Pascal's triangle came from. If you already have a Pascal's triangle made, then you've got all these numbers already done. If you don't, then you'd have to create it to the 8th row, and that might take us a little bit of time, but we could get there. And I want to look at one other thing about Pascal's triangle, and I'm going to go ahead and build a little one up here. If you had 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and I'm only going to make it to the 4th row here. But if you look at the sum of each one of these rows, the sum of that row, it's called row 0, is 1, and then the sum of the next row is 2, and then the sum of the next row is 4, and the sum of this row is 8, and the sum of this row is 10, 14, 16. Do you start to notice a pattern here? Okay, you maybe learned this from your college algebra class, or perhaps not, but it works out pretty slick. If you're looking for the sum of the numbers in that row, these are all just powers of 2. Yes, it doubles from here to here, and it doubles, and it doubles, and it doubles. But if I wanted to jump down, let's say, to the 8th row, it's more than it's just doubling, because I don't want to have to know the 7th row and the 6th row. I want to know this number by itself. Well, this is the 4th row, and this happens to be 2 to the 4th power. This is the 3rd row. This happens to be 2 to the 3rd power. This is the 2nd row. That's 2 to the 2nd. Oh, so if I want to know the sum of the 8th row way down here, it really would just equal 2 to the 8th power. That's actually kind of handy because that just took away all that work I was talking about having to find all those answers or building this to the 8th row. The 8th row is 2 to the 8th, the sum of the 8th row. Well, I can do that quickly in my calculator then. Now I've got my answer. Okay, there are 256 different sandwiches possible. And that didn't take me any work whatsoever. That's handy. If you want to know the total number of ways something like that could happen, it's just going to be 2 to the whatever power that is. If there were 13 different toppings, then it would be a 2 to the 13 for the total number of ways. Let's make this a little bit trickier. How many sandwich toppings are possible if I choose at least? Boy, that makes it a little tricky right there. The at least 3 toppings. If you said exactly 3 toppings, I would just do 8 choose 3. But saying at least 3 toppings means 3 or 4 or 5 or 6 or 7 or 8 and so forth. Now, probably what's going to happen then, and 8 isn't too bad. I've already got my Pascal's triangle built to the 4th row. I could probably make it to the 8th row, but here's what you want to do. you want to think of it as, okay, there's a choose 0, there's a choose 1, there's a choose 2, choose 3, choose 4, choose 5, choose 6, choose 7, choose 8. Those are all the different ones. And I am looking at picking at least 3. That means at least 3 or 4 or 5 or 6 or 7 or 8. I want all of that. I just want a piece of this. So I would have to do all of these combinations, the choose 3, the choose 4, the choose 5, choose 6, choose 7, choose 8, and then I'd have to add those all up. But since I already know the total, I mean, and I could do that, but since I know the total, I'm looking at this, and wouldn't it be easier to find what it can't be and just subtract it from that total? I think I would do that. I'm going to go ahead then and do the 8 choose 0, the 8 choose 1, and the 8 choose 2. That's what I don't want it to be, right? And then I'm just going to take 256 and subtract that. The other thing that's handy about that is those 3 things that I want to find right there are really super easy to find. If you think about your Pascal's triangle up here, 8 choose 0, well, anything choose 0 is always starts off at 1. I already know that that's going to be a 1. That's what that equals. And 8 choose 1, if you look at the second number of Pascal's triangle, is always the number itself. I already know that that's an 8, so that's not going to be hard. And 8 choose 2, okay, maybe I don't know that one. So then I type 1 in my calculator, and I do 8 math combinations of choosing 2. Oh, that's 28. And then I can add those all up. So that's 9, that's 37. I would take 256, which is my total, subtract what I don't want it to be. Okay, I should have done that in my head, I'm sorry. Do mental math. 219 ways to make a sandwich with at least 3 toppings. I chose to do this subtraction because the things that I did want were a lot more than what I didn't want. If this was the other way and I said at least 6 toppings, and that would mean 6, 7, or 8, I'd be better off just to do the 6, 7, or 8 than to do this subtraction thing that I just did here. You have to pay attention to what they're asking to find out what the simplest way to do that problem is. Okay, so that's a place where we can use those combinations. It can be a little bit deeper thinking. So this is the last thing. I just wanted to throw some sample problems at you, see if you can use those 3 different things, the fundamental counting principle, permutations, and combinations. Decide which one should be used in these different situations. I'm going to let you go ahead and pause the video and work through those 5 problems, and then come back when you're done. All right, let's quickly go through these. On the first one, you're just doing your fundamental counting principle, how many ways to do something, times how many ways to do the next thing, times how many ways to do the next thing. On number 2, the reason that the dice are different colors is just to distinguish them from one another, so to recognize it's kind of like order is important, that your one dice is different than the next. I guess is the easiest way to say. I would have typed that in 6 to the 3rd power on my calculator. Number 3, you're doing card hands. Order is not important when you're playing cards. I just have 52 cards in the deck. I'm going to choose 7 of them. The answer key problem, this is similar to how we had done that one earlier. There's 4 options for the first question, 4 for the next, 4 for the next, and so forth. Okay, the Panda Express problem is the one like the Subway problem. There's 15 different entrees, and you can have 1 or 2 or 3. How many meals could I create? Well, I want to have at least 1, otherwise I'm not eating. So that's why I didn't have a 15 choose 0 here. And this was definitely easier for me to do what they wanted as opposed to do what they didn't want. It was 1 or 2 or 3. Okay, so I'm going to do these simple ones. 15 choose 1 I know is just 15. I put this into my calculator to get 105. And then as a shortcut, if you're going to do this type of problem, it's really not too bad in your calculator because you can just do like second enter, or some calculators you just arrow up and press enter on it, and it brings that 15 choose 2 back and just change it to a 3. And you can really do several of those very quickly. I ended up with 575. All right, go try this on your homework. Good luck.